We dope p-type impurities like boron on the left half of one slice. Boron atom, being trivalent, accepts one electron from the neighboring silicon atom and creates a vacancy or hole in the silicon structure. As boron accepts one electron, it loses its neutrality and becomes negatively charged ion. These ions are immobile in nature. Thus we have holes and negative ions which are formed in the left half, which forms the anode and acts as a positive terminal. The n-type impurities are doped onto the other half of the same slice. When we add the pentavalent atoms like phosphorus to the silicon slice, they form four bonds with four neighboring atoms of silicon, and we get one electron that remains free. As the phosphorus atom donates one electron, it loses its neutrality and becomes a positively charged immobile ion. The N region has free electrons and positive ions. This terminal is called as cathode, and it acts as a negative terminal. As a result of this doping, an electrical isolation is formed between the two regions, which depict a junction. The symbol of the diode is as shown. Let's understand the working of a diode. The electrons from the N side get attracted towards the holes of the P side. These electrons cross over the junction, recombine with the holes, and cease to be free carriers. This process is called as diffusion. This process of recombination continues for some time, but remains restricted near the junction only. As free electrons and holes get depleted from the region near the junction, this region is called as the depletion region. Depletion region contains only negative ions on P side and positive ions on N side of the junction. These ions are immobile. The motion of electrons doesn't stop immediately after the formation of the depletion region, but as they cross the junction, they get repelled by negative ions on the P side. Hence, at this point, motion of the electrons stops. These charged ions develop an electric field in the depletion region known as junction potential. Junction potential is 0.6 volts for silicon and 0.2 volts for germanium. Junction potential restricts electrons from crossing the junction further. When external voltage greater than the junction potential is applied to these electrons, they overcome the opposition of junction potential. This process of applying external voltage to an electronic device or a system to establish suitable working conditions is called as biasing. The word biasing is used to depict the inclination or preference towards a particular side. The diode is inclined or biased either in the forward direction or in the reverse direction. Thus, diodes are operated in two modes: forward bias and reverse bias.
Seriously, pay attention. This is important.
We first look at the forward bias operation of the diode. We connect the positive terminal of a battery to the anode and the negative terminal to the cathode of a p-n junction diode. Internally, this positive potential to P side repels free holes towards the junction, and negative potential to N side repels free electrons towards the junction. As we increase the amount of external voltage applied, electrons try to break the electric field at depletion region to enter into the P region. As we increase the voltage over the junction potential value, electrons from N side of the diode attain enough energy to break the electric field and cross over to the other side of the junction. Thus, electrons move from cathode to anode, setting up the flow of current from anode to cathode. This mode of operation is called as forward bias, and this current is called as a drift current. In the second case, we apply the battery in reverse direction. That is, we apply positive of the battery to cathode and negative of the battery to anode. As a result, holes are formed towards the negative of the battery, and electrons from N side are pulled towards positive of the battery. Thus, holes and electrons move away from the junction, which leads to an increase in the depletion region width. No current flows through the diode. This mode is called as reverse bias mode. But there are some minority charge carriers always present in both the regions. Hence, in the reverse bias case, minority charge carriers cross the depletion region, setting up the current flow. But magnitude of this current is very low, in nanoampere range. Ideally, in the reverse bias mode, current through the diode must be zero. But practically, we get some current which is called as the leakage current. Let's study the characteristics of this diode. This graph is drawn by considering external applied potential on x-axis, current flowing through the diode on y-axis. When the diode is operated in forward bias mode, current flowing through the diode between A and B remains at a low level. But as soon as the external voltage crosses the junction potential value, or cut in voltage, the flow of the current rises from point B and point C. This graph is called as the forward characteristics of a diode. When we connect the diode in reverse bias, the leakage current flows in the opposite direction till point D. But if we further increase the reverse voltage applied at one point, diode breaks down and a large amount of reverse current flows through it, which may damage the component. This value of reverse voltage is called as the breakdown voltage. In order to prevent our diode from breaking down, the diode should be doped in a very controlled manner. When an ordinary diode is heavily doped so that it has a very sharp breakdown voltage, it is called as the Zener diode. Thus, in the Zener diode, the breakdown voltage is accurately adjusted to make it withstand in the reverse biased mode. Hence, the Zener diode works effectively in reverse bias also. Due to this special characteristic, the Zener diode finds many applications in the voltage regulator circuits. The symbol and characteristics of the Zener diode are as shown. Thus, the only difference we get in these two types of diodes is that the PN junction diode doesn't work effectively in the reverse bias mode, increasing the probability of failure or breaking of component, whereas the Zener diode is specially used where controlled reverse bias operations are required, thus eliminating chances of component failure. There are many types of diodes available in the market which look identical but differ in their performance parameters. So how do we select the best type of diode suitable for use? We select them according to their specifications like DC resistance, AC resistance, diffusion capacitance, and transition capacitance, etc. Let's see what these parameters are. When the diode is operated in the DC voltage, the resistance of the diode is called as DC or static resistance. From the characteristics of the diode, this resistance is calculated by the ratio of V upon I. As DC source remains constant, we can compute V upon I ratio throughout the characteristics graph. During forward bias, current through the diode increases with the applied voltage. Hence, as the diode starts conducting, its resistance value goes down. Thus, during forward bias, the diode has minimum resistance. On the other hand, this resistance takes a very high value of mega ohms during reverse bias. DC or static resistance plays a vital role in the analysis of clipping circuits or rectifier circuits. When we operate the diode on the AC signal, its resistance does not remain same as that of DC or static resistance. This is because AC signals continuously change in a sinusoidal manner along the axis, taking alternate positive and negative values. Thus, this resistance becomes dynamic in nature. This dynamic resistance is calculated as dV upon dI. This dynamic resistance comes in picture as an important parameter when we deal with the analysis of circuits that work on AC signals. During forward and reverse bias, the diode exhibits two types of capacitances: diffusion capacitance and transition capacitance. During forward bias, free electrons from N side cross over to P side, resulting in change in charge. This motion of electrons depends upon applied voltage. Therefore, diffusion capacitance is defined as the change in charge due to change in voltage during forward bias operation of the diode. CD equals dq upon dV. During reverse bias, we get change in a charge as majority charge carriers move away from the junction, leading to the capacitance called as transition capacitance, defined as change in charge due to change in voltage. CT equals dq upon dV. Let's have a quick review of what we've studied in this lecture. William Henry Eccles was the first who coined the term diode in 1919. Diode nomenclature is derived from the Greek roots as di meaning two and ode meaning electrodes. The diode is a semiconductor device formed by doping the p and n-type extrinsic semiconductors into pure silicon or germanium semiconductor. A junction formed between p and n regions of the diode find many applications in electronics, as the diode is used as a switch or in rectifiers. When the diode is in forward biased, its equivalent resistance decreases to few ohms, and the diode allows the current flow, hence it acts as a closed switch. When the diode is in reverse bias, its equivalent resistance attains a very high value of few mega ohms, 10 raised to 6 ohms, and blocks the current, acting as an open switch. There are two types of capacitances associated with the diodes: diffusion capacitance when diode is operated in forward bias, and transition capacitance observed during reverse bias. Zener diode is a heavily doped p-n junction diode, which is specially used for its current conduction in reverse bias method and controlled breakdown voltage.